preparing this talk that this is the first year that I've been doing ICS malware analysis longer than I did Windows stuff. So now this has just become my thing. And so I decided it would be cool to sort of talk about the big ICS malware events for the past 7 or 8 years and what it was like to analyze them and what it can teach us about ICS and ICS malware analysis. I know that a lot of people here might not be critical infrastructure folks. So just to get started, ICS means industrial control systems. That's the term for the electronic devices that support electronic, industrial process control. It can be one system that takes measurements from sensors like pressure or temperature, or it can be a huge network of systems. But the goal here is to do something physical, refine oil, distribute electricity, move mining slurry, make cereal. Operational technology is the word that we use to distinguish the networks that contain these devices from IT networks. Primarily, this term is there because those networks have different kinds of devices, different kinds of protocols, and just have a different responsibility because they're just closer to physics. And so with that out of the way, let's get started here. I started at Dragos in 2017. I applied for a Vol analyst job, and they said no. And they said we needed a malware analyst. So I ended up becoming a malware analyst there, and I had no experience with ICS. In the job interview, they were like, what do you know about ICS? And I was like, well, I've heard the word SCADA, and I know Stuxnet was in the news. And so I had a lot of stuff I had to learn on the job. And what I realized was I had a lot of assumptions sort of going in to ICS, the ICS space in general, and what malware analysis would look like. And those things ended up being misconceptions. And I thought for this talk, it'd be really interesting if we talked about some of those misconceptions alongside example malware families that sort of illustrate what reality is. And then sort of after that, we'll talk about what that can teach us about ICS and malware analysis in general. So the first misconception is that ICS malware analysis is an independent skill set. Before Dragos, I sort of considered this world as like this extra magic box, like this sort of like Narnia of embedded firmware analysis and things. And I want to talk about sort of the first piece of malware that I had to deal with, which was TRISIS. This is literally the first thing I looked at my first day on the job. Like Friday before I started, I didn't have a laptop, and they contacted me and said, hey, we have something you need to look at. And I was like, I don't have a laptop, so we need to wait. And then Monday morning, they said, get set up, and then they handed me this. So TRISIS was the first malware to attack a safety instrumented system or a safety controller. A safety controller's job is to monitor an industrial process and make sure that it stays within safe parameters. So on the screen there's that stack with a flame coming out. That's known as a flare stack. If you look at a petroleum refinery or offshore oil rig or something, you'll see these. And what they worry about with these processes is that the pipes might become overpressured. All of these pipes are rated for a certain temperature and pressure. And if that gets too high, or the pressure gets too high or it gets too hot, bad things can happen. So a safety system will monitor this process, check the pressure, make sure everything stays safe. And if it ever gets too high and it gets too close to that limit, they'll stop the process. The safety system will stop. It'll bleed off the extra gas, and then that's where the flame comes from, because it burns it off to relieve the pressure. It'll wait a while, and then restart the process. If an adversary wanted to do something bad, it wouldn't be enough to create a situation where the pipe overpressures, because the safety system and the pressure control valves and things will catch that and bleed it off. So if you want to attack a place like this, you have to create the situation where the overpressuring will happen, but you also have to bypass the safety system. And this is why TRISIS was a big deal, because it was the first malware to ever even hint at doing this kind of attack. Analyzing it was difficult, just because there were a lot of pieces and a lot of extra stuff that we had to do. The main part of it was Python. It was compiled Python py-to-exe script that was like an installer. Basically, it sent the PowerPC payloads over to the controller. There was a library that implemented the custom protocol, the tri-station protocol for speaking to this triconic safety system. And then there were 3 PowerPC payloads. The first one, the preset payload, very simple, sets a count variable on the controller. The second 2 was an exploit and a rootkit. The rootkit's job, the exploit runs on the firmware, and it exploited the system call handler to install essentially an extra network command on the firmware. That network command allowed arbitrary code execution on the controller despite this config protection scheme called a run key. So there's like a physical key on the controller. There's a program mode and a run mode. In program mode, you can upload code, you can change the configuration. It's a mode the controller runs in when you're setting things up. when you're ready to commission the system and deploy it and have it be in the environment and doing whatever it is it's supposed to do, you put the key back into run mode, no more changes allowed, right? The way this rootkit worked was no matter the state of the key switch, because that key switch is basically checked in software. So you send some bytes, the function that handles that network command just goes, is the key switch in run mode? No? OK, cool, you can do that. And so they just implemented a command that didn't check the key switch, and then they could arbitrarily execute code despite what setting the key was in. And so when we looked at I have a pointer, right? Yeah. So when we looked at the exploit in the rootkit, we realized really quickly that we had to figure out like what the controller looked like. And so that involves some hardware reverse engineering, desoldering memory, scraping conformal coding, extracting the firmware, and then analyzing the operating system. For this task, we had to go through like all levels of reverse engineering. There was like basic Python analysis and decompilation. We had PowerPC analysis and reverse engineering, hardware reverse engineering to analyze the board and extract the firmware, firmware and operating system analysis. We had to look at the system call handler and other parts of the firmware to understand how the exploit interacted with it. There was protocol analysis to make sure that whatever traffic was being emitted by the malware, like we had to check it against what was being emitted by the Schneider Electric software that talked to the controller, line it up, make detections, right? So this is a key part of defense, right? And then the engineer's knowledge, which is like real basic stuff that we don't think about, but we don't know how to set up these controllers, so we have to learn that stuff or talk to somebody that knows how to do it. So what do we buy? How do we run it? Right? How do we even set it up and get it running? And so we had 5 or 6 levels of RE. And so the reality here, and I remember thinking, I was like, wow, this is like that New Game Plus mode in like Elden Ring. It's like you have to take all the stuff you know about operating systems, programming languages, assembly languages, and the like, and just be ready to apply that to any kind of architecture or system. So for example, Rockwell devices have their own logic and runtime system and interpreted assembly language and everything else. So if this attack had happened on a Rockwell system, we would have had a custom program, a custom assembly language that we didn't know how to interpret. So we'd have to understand the controller, plus a new runtime, plus the assembly language, plus what the actual program was having to do. So it's not like Windows where we all kind of come in with this base level understanding of how the API calls work. You sometimes have to look at like program all the way down to the hardware to understand what's going to happen when this malware runs. The next misconception is that you can be an expert in ICS. After we finished analyzing TRISIS, they asked me to go back and look at Crash Override. Crash Override was a piece of malware that was used in an attack against Ukraine in 2016. It took out power to a neighborhood for about 2 or 3 hours until they reset things with manual controls. This one is a little bit more straightforward. It was just regular Windows malware, execution-wise. It was a collection of launchers, and they would, when executed, they would launch a separate DLL. There was one DLL for a particular network protocol, so IEC 101, IEC 104, IEC 61850, OPCDA. All of these protocols were for talking to the intermediate, well, the protocols, no, the DLLs were for talking to the intermediary devices that controlled breakers or switchgear on the transmission substation. And basically when they ran, they would tell the breakers and switchgear to turn off and on again, right? And just like the breakers at your house, if you turn the breaker off, everything goes out. And that's basically what they did to this transmission substation in a more complex way. Now, I looked at two of those DLLs. The OPCDA module was primarily used a third-party library that I could find online, and I could just map that up to the assembly, look at the API calls, everything's good. The 61850 MMS module, it was like beforehand they used Wireshark and just captured the traffic, and they looked at what bytes moved when they changed IP addresses and targets. And so they copied and pasted all the static bytes and then built the response by hand, which is what you see here with this like kind of dereference of RESP and this XMM word, right? They're just kind of copying bytes over. I guess I could have set this to like read only, so IDA would populate it as a string, but close enough. Now, I had no idea what this protocol looked like, and I started looking at specification docs trying to figure out what was going on. This is a reference that Wikipedia uses for 61850, and it's a slideshow by the Illinois Security Lab. And it's only 10 parts, and they tell you that you only have to read like 7 units or whatever to understand what this protocol is. And then all of the stuff for the protocol is written as if you're like a power engineer, right? Which I'm not, okay? So when I was going to analyze this malware, a lot of it was like, okay, I'm kind of making some guesses. And you kind of have to stick to like the basics, like what are my inputs, what are my outputs. You know, if I was trying to change the state of a breaker, there has to be a variable that represents the breaker state. It's probably a Boolean, that'll be off or on. Which one of these values is going to be that, right? Let me just try to find where they're going to set probably a 0 or 1 or a true or false, and then kind of backtrack from there. And you're sort of like doing those kinds of things because you don't actually know which value they would change. Because I don't know how to do a power systems attack, right? And so I was looking at all this, pretty confusing. And so what did I do? Well, it turns out that Dragos has a really good relationship with Schweitzer Engineering Laboratories. So more than likely, the distribution and power stations here in DC probably have equipment from Schweitzer Engineering. They are like big power systems nerds. They started in 1984 after their founder, Dr. Edmund Schweitzer, invented the first digital microprocessor-based protective relay. Right? These are basically systems for finding faults in power lines. And so I wrote my report, and I sent it over to them. And I was like, guys, can you take a look at this and you know, let me know if this sounds right to you? Like, what do you think? And they got a bunch of like PhDs and power systems nerds on the phone with me. And they just walked me through the whole process. They're like, no, you're talking about this the wrong way. That's the wrong protocol. Don't use that language, like blah, blah, and just like fully redlined the whole thing and helped me get it right. It was awesome. And so, but what did this teach me? Well, for this one piece of malware, I had to learn about basically 3 or 4 different protocols about breakers and switchgears in general and electric transmission facilities. That's one very small sliver of what the electric industry is as a whole. Right? We're not even talking about like distribution to your neighborhood. We're not talking about how they generate the electricity to begin with. We're talking about the intermediate step, when it comes from the place that generates the electricity and is trying to move the electricity from there to like your local distribution station in your neighborhood. There was no way I was going to be an electric industry expert, right? And I was thinking, well, I work at Dragos. They're supposed to be covering all critical infrastructure. How am I supposed to know all the stuff I'm supposed to know for food and beverage and nuclear and oil and gas and, you know, all the number of automotive, you know, I like to joke cereal, dog food making, all of these things that we consider critical in some sense. It's like, I'm just not going to. And generally speaking, even in the media, none of those guys know what they're talking about in that sense. There's no such thing as an expert in ICS. If someone tells you that, it's like they're saying they're an expert in science. It just doesn't make any sense. The next misconception is that ICS malware is the only threat to ICS. So after we finished with crash override in I looked at that 2018. By 2019, the ransomware stuff had like really kicked off, especially when it came to the industrial space. And the first big one that I could remember when I was writing this talk was the Norsk Hydro attack by Locker Goga. So at the time, Locker Goga ransomed Norsk Hydro. They're a Norwegian aluminum manufacturer. And at the time, the CFO said something like, you know, our entire network is down, the office and productions had been stopped, the whole 9 yards. And a little after that, Ekans happened. And Ekans caused a big stink. Everyone was calling it ICS ransomware, malware targeting ICS. You know, these are all sort of the headlines and such. Even though it had no real ICS capabilities, but it was kind of an interesting time in that sense. So what Ekans did was, it had like a big process list. It was just a big dump of process names. And it basically looped through all of them and called terminate process. Like that was it. And inside of that, there were like hundreds of these. Inside of that, there were like 2 that were licensing servers that happened to be maybe affiliated with some ICS software. And they took those 2 process names out of 100, and it became these headlines, you know, like this kind of thing. It's like, well, this is hardly it's targeting that plus SQL, like whatever. But this was still it caused an interesting debate. Because at the time, Dragos wasn't really tracking ransomware. And we didn't want to, right? And on that side of the debate, there were people like me that were like, dude, there are AV companies. Like, let them handle it. This is their bread and butter. They know what they're doing. And then on the other side of the debate were the folks that were saying, we got to do something about this. Like, it's attacking our customers. They care. They want to know our opinion. And those AV companies aren't inside of these OT networks, right? We are. So we have to have like an opinion on it. So the latter one, and I lost, and which meant I had to analyze a lot of ransomware. But what I learned was that, you know, when you're looking at the threat landscape for ICS, it's anything that can negatively affect ICS that matters, right? All of the things, you know, there are threats, right? Overarching category, and then ICS malware is this really, really tiny sliver of all the things that actually harm an industrial site. And so they have to worry about the things that are OT specific, as well as all of these IT threats that every other enterprise cares about, right? So it's sort of like double. Maybe like the risk calculus is a lot different. And in ICS, even attacks to the IT network can affect operations on the OT side, which we all saw in the Colonial Pipeline attack in 2021, right? The IT network didn't actually, the IT network got ransomed, but the OT network didn't. But because the IT network got ransomed, they couldn't build customers, so they shut down the pipeline, because if you can't, I mean, come on, man, it's oil and gas, right? Like, if you can't spend, you got to make money. But also what they were worried about was, and that they might have stolen some information that would help them attack the pipeline. So they're like, all right, we need to shut things down until we figure this situation out. So for ICS malware analysis, what that means is that we have to look at not just the ICS malware stuff, but hacktivists, the ransomware people, script kiddies, on top of the stuff that we maybe more classically associate, and the stuff that before Ekans we were thinking about in terms of threats, which is the APT-style tools, and then the stuff like your TRISIS and Stuxnets and crash overrides that are actual ICS malware. The next misconception, that ICS malware analysis is a singular job role. So the ransomware stuff was basically 2019 to 2021, and still ongoing. I'm not saying it went away. But in early 2022, we got tipped off by a source to Pipedream, and shortly after that, ESET and Ukrainian CERT discovered InDestroyer 2. They stopped it before it got on the network. Pipedream is an umbrella tool for 5 different pieces of malware for attacking ICS networks. Now, there's a talk from like 2 years ago at DEF CON that goes into this in a lot of detail, and I don't have time to cover all 5 of these in detail. So what I will say is Evil Scholar and Bad Omen are basically a malware author's engineering software. Both of them allow you to do all kinds of things to a PLC. So Evil Scholar uses a codesys protocol. Codesys is a very popular industrial protocol and runtime system used by hundreds of vendors on thousands and tens of thousands of devices across all kinds of industries. You can log into the device, you can download new code, you can sever connections, you can DOS the device, you can proxy traffic through one of the controllers to bypass industrial firewalls. Like, there's like all sorts of stuff that this kit can do. Bad Omen is similar to Evil Scholar, but it only attacks Omron devices using their next HTTP protocol. Bad Omen basically has the same functionality that Evil Scholar has for codesys devices, but on Omron stuff, but with the added complexity of being able to target servo devices. So servos are basically a motor that spins a shaft. So, I don't know, robot arms use servos. Dam wickets, things that open and close in a dam, use servos. Drones to move the camera use servos, right? Basically, if you require some movement, it probably uses a servo. And then you had Dust Tunnel and Lazy Cargo. Dust Tunnel and Lazy Cargo were Windows malware. Dust Tunnel is a standard implant that uses secure comms, not too complicated. Lazy Cargo is a weaponized version of an open source ASRock motherboard vulnerability for loading an unsigned driver. Shortly, while we were analyzing Pipedream, InDestroyer 2 got released. I won't spend a whole lot of time on this. InDestroyer 2 is basically a new variant of the IEC 104 component of crash override. So they took that DLL, they changed some things about the IEC 104 piece and some configs, wrapped it up in an executable, and that was InDestroyer 2. I don't know that it's different enough to actually give it its own name and not just call it like crash override again, but you know, whoever discovers it names it, so this is what we're stuck with. It's InDestroyer 2. Now, we had 6 pieces of malware and 3 reports to get out in like a month. So this was like an all hands on deck situation. We had 5 reverse engineers working on this in pairs. One person was hands on keyboard, restoring controllers and the like. The other person was like running the malware, making sure everything worked. We reached out to external friends to help us find the controllers that we needed. We talked to internal plant engineers to help us set everything up. We had to set up, I think, 4 different controllers at least. Plus, we had a mock pipeline set up, like with a big old water tank and stuff, to test some of this stuff to make sure it actually worked as advertised. It was basically like months of effort condensed into 1 month. And the reality here is that ICS malware analyst doesn't really exist as an individual role. Like even at Dragos, like that's not my title, right? My title is that big, long, complicated thing, but it's basically malware analyst. The reason for that is that you just can't know enough, right? There's just no way for one person to understand all the things. So if you imagine you're trying to hire a software reverse engineer and just the requirements that go with that, which is programming languages, operating systems, networking, API, assembly language, knows IDA or Ghidra or Binary Ninja or whatever, and that's like your baseline. And then you say, okay, well it's kind of like embedded, so now we're going to add hardware reverse engineering. So now that person has to know how to, solder, desolder memory, We add the firmware reverse engineering. They understand how to analyze firmware, find all the entry points, interrupts, all that really low-level stuff that comes with firmware. And then on top of all of that, you add all the ICS engineering knowledge. Knows how to set up and operate any number of PLCs from any of the 100 vendors, which I guess you have to specify in the job listing. So we'll go with Rockwell, which has, I don't know, a product line of hundreds of PLCs across industries, probably thousands. And then knows and understands things like, I don't know, voltage requirements for equipment, knows how to set up and configure things like servos, elevators, conveyor belts, whatever else. Any number of logics and runtimes, like I was describing before, because you can have custom interpreted assembly languages and the like, right? And the list goes on. As I keep building that list, I'm more and more just describing an imaginary person, right? Like no one's going to be able to do this. And so you have to have a cross-disciplinary team to work on this. And I'm not even talking about the industry knowledge that would be required, right? That we have to lean on and ask questions about, like, I don't know, how does nuclear generation work, right? What is that big, large tank in this picture for? Right? And you have to have those people on staff somewhere. All right, the last misconception, that ICS malware is obvious. And so Pipedream 2022, released that, did all that stuff. We came into 2023, and if you had asked me before that, before 2023, what is ICS malware? I'd have said, well, it's those 7 things that we know about. That's ICS malware. We've got Stuxnet, Havix, Black Energy, Crash Override, Pipedream, that list. I feel like I'm missing 1 or 2, but either way, we had about 7 up until 2022. Like that's it. You don't have to ask anymore. We don't need to define it in any kind of sense because we don't really have that many to begin with. But as we started hunting and other companies started to discover stuff, it made us question a little bit like what we considered ICS malware, and it just caused us to think about these things more. And I think, for me, the turning point was when Mandiant released this report on cosmic energy. So they were hunting, I think, in VirusTool. This is shortly after they got acquired by Google. And they found this piece of malware, and they put forth that it was IEC 104 malware. So again, that's an electric protocol, can manipulate breakers and switchgears and the like. And that this was IEC 104 malware for simulated power disruption exercises in Russia. Right? And that does sound really scary. We looked at it and analyzed it, and we downplayed the threat, and we did not apply the term ICS malware to it. Because when we looked at it, it looked like they had just taken a GitHub sample project and they just had copied and pasted and changed a couple of values. And I'm like, well, right? And we didn't have any evidence that it was meant to be deployed anywhere. We didn't, basically we couldn't find any evidence of malicious intent inside of this thing. And that's kind of a key part of malware, right? You have to know that the thing is going to be used for badness or you can't say anything. Now, I'm not saying this because I actually think Mandiant was wrong and Dragos is right or the other way around. That's not the point here. The point is, ICS malware is a pretty big concept and it's a pretty important concept. And this is the first time that we had ever even stopped to be like, oh shit, we don't agree with somebody. Like back when we did TRISIS, we didn't argue about whether or not it was ICS malware. Everyone's like, yeah, that's definitely ICS malware. But when it came to this, suddenly everyone's like, wait a minute, wait, is it? Right? And so this is a real interesting turning point for us. In 2023, we were hunting, we found FrostyGoop, and with information from the Security Service of Ukraine, we were able to link it to an attack, a winter attack that took out heat. It was an attack against a municipal energy company. It affected, it took the heat, disabled the heating systems, and it affected like hundreds of people in 600 apartment buildings, right, in the middle of winter for 2 days, I think, in Lviv. Sorry, I don't have my notes. I'm doing a lot of this from memory. It's tough. So we thought it was pretty obvious this thing was malware. And with cosmic energy, it was sort of an internal debate, right? We're like, oh, do we call this malware? We're like, is this bad? Right? Okay. Well, with FrostyGoop, we were getting a lot of questions from our customers now. They were asking us questions like, well, it uses Modbus. Like, how can that be malware? Like, Modbus TCP, like, is this really malware? Things like that. And I was like, well, that's kind of like saying, can this be malware because it uses HTTP? Like, that's silly, right? So just because it's a known protocol doesn't mean it can't be malware. We were getting questions like, well, if FrostyGoop is malware, well, why isn't Metasploit's Modbus modules malware, right? And I'm like, well, Because Metasploit's not malware, right? Like we don't look at a red team tool and call it malware. But it's a pretty fundamental misunderstanding to get a question about, right? So, and the last one I think was one of the other big ones. It was that, how can this be the first Modbus malware? Like, aren't you all like overhyping it? And I kind of understand. I want to say that was like a LinkedIn post or a tweet. I can't remember what it was, but I can kind of understand their incredulity, because when you look up ICS research, I mean, there are dozens, probably hundreds of papers on ICS research and controllers, and so many of them are just Modbus. Like, Modbus TCP has been ripped to shreds. Everybody knows that the unencrypted version of this protocol is not secure, that it can be attacked, it's, no authentication, whatever, right? So to them, they were like, well, all this research has been done. All of that stuff must be the first Modbus malware. And I'm just kind of like, well, that's just not how things work. Like I don't control the adversary's timeline. Like, if you're mad that this thing hasn't been released on time, I don't know, go talk to them. Go deal with their changelogs and version history. And you put a GitHub request to the adversary for not releasing the Modbus malware in time for you or whatever. But the fact is, this is the first one we've seen. And for us, it was really obvious, right? We have custom development. There was custom development. It did really bad things to a real-life site. And we have corroborated information from a trusted source. All of those things line up to being Modbus malware and the first one. While we were doing our own internal hunting, though, we started asking a lot of questions, too. We'd find something and be like, oh, is this ICS malware? Or is this ICS research? Is this ICS malware? Or is this an ICS red team tool that we're discovering from another country? And these questions kept cropping up, and we started to have more and more debates about it, which is super interesting. And I remember actually taking a step back and thinking, like, why are we arguing so much on this team about this stuff? I don't remember any of these arguments before. Like, back in 2018, we were arguing about stuff like that. Well, first thing was, I was the only malware analyst in 2018, so I'd been arguing myself, so that doesn't happen. But also, it's just that we have more stuff now, right? So if you think about the timeline here, Stuxnet was in 2010, and from 2010 till 2021, we had 5 pieces of ICS malware. And then from 2022 through 2024, we added 4 more. And that was it. So we just didn't have enough data in the initial time frame to even consider that. And now we've added 4 more in less than 3 years, and we're discovering all kinds of candidates that might fit the bill, or we'll put in like a potential ICS malware category and then track them. Because if a couple things change, or if something changes about the malware, maybe add an extra capability, or we actually see it get deployed or something, we're like, oh, well, then that's definitely malware. But there's not enough evidence in the code for us to absolutely be sure. Because if we raise a stink about it, it makes like news and stuff. So we don't want to like make a mistake, and we don't want to get people scared for no reason, right? So we just didn't have enough data then to really consider these big questions, and now we do. And we are asking these questions. And from an academic perspective, that's really interesting, being on the edge of this. Like, what is ICS malware? What are we going to call it? What are the requirements for these things? As a human person that relies on water treatment and electricity just to live their lives, it's kind of scary, and I don't like it. But when you view it from this sort of like timeline and data perspective, we're only now at a point where we can start thinking about those larger things. So what are the takeaways from all of this? Well, I think most of this talk is about ICS malware analysis being a team, right? To reiterate, you need to understand the industry knowledge, all the different verticals, on top of just like leveling up reverse engineering, and just have lots of different folks with different backgrounds to make it work. It has to be a cross-disciplinary effort. I don't think, there's just no way we could have gotten through all of these things without multiple people and having folks that I could just lean on to ask questions about certain kinds of industries. So to put things in perspective, when we analyzed TRISIS in 2017, I think Dragos might have had like 30 people. 33 people helped me analyze and supported the analysis of pipe dream in terms of the actual raw analysis, reverse engineering, but also just industry-related questions and reaching out to folks. Even, we even worked with like Omron a little bit, some of the vendors and things. I mean, there were a ton of people involved in that process, and I don't think we would have gotten it done without their help. And the last takeaway is that ICS malware analysis is still new. So the first virus, maybe, I don't know, I feel like this might be debatable, but as far as I can tell, the first virus was Creeper in 1971. It was some kind of ARPANET thing. And if you think about where the beginning of malware analysis is, and you're conservative about it, I would say it's probably the 1984 paper by Fred Cohen, where he describes what a computer virus is. And he defines certain problems about antivirus and detection, like, detecting a denial of service program is equivalent to the halting problem, so it's NP complete. He does all kinds of stuff like that. If you've never read this paper, the short story is Fred Cohen in 1984 said, if you're a malware analyst, you're going to have job security for probably 100 years. Is basically what this paper is. But that is the start of like modern malware analysis, I think. So that was 40 years ago. And since then, we have 1 billion plus malware samples to go off of. Whereas in the ICS space, we started in 2010 with 1 sample, and we have 9 total now. And I maybe have a handful of other candidates to consider, right? And so there just isn't enough yet, right? And we're still learning a lot about what it looks like, how we're going to take things apart, the kinds of capabilities, and the degree of sophistication. And we're learning on our side, on the defensive side, but we also think like the adversaries are probably learning this too. Especially when you look at some of the tooling, like that first crash override where they copy and pasted bytes in. Like they're clearly getting their shit together too. So still a new field. Anyway, thanks for coming to my talk. I hope that I piqued your interest in industrial control systems and this kind of malware analysis. It's a fun gig. I really enjoy it. That's my dog, Velma, that Steve mentioned earlier. I'll be around for the happy hour networking event later. So if you have any questions, feel free to reach out. Yeah.